All right, so one order of business, there is supposed to be a lab today. We are just going to straight not do it. Since I wasn't here on Friday to do Thevenin and Norton equivalent circuits, my grad student Nolan was. I'm going to spend a little bit of extra time today with you guys just to make sure that everything is nailed down, and then we'll go from there. So this is Thevenin and Norton equivalent circuits 2. And today we are going to investigate what happens when there are dependent sources in our circuits. So we're going to start by looking at this circuit in which we have a 20-volt source connected to a 6-ohm resistor, which is in turn connected to a current controlled voltage source. So let's call this 2ix. Let's have a 6-ohm resistor like so, and define our current Ix as the current flowing down through this particular 6-ohm resistor. Then over here, we have a 10-ohm resistor. And across our bottom thing here, we have an open circuit. I am copying this just so that I don't have to redraw it over and over again. Okay, so this is the circuit that we are going to be analyzing, and we are going to talk about how to find the Thevenin equivalent voltage, the Norton equivalent current, and the Thevenin equivalent resistance in several different ways, okay? The Thevenin equivalent voltage and the Norton equivalent current are going to be exactly what we did, or what you guys did last Friday. So if we wanted to find VTH for this circuit, what would we do? And we're finding it between the open circuit terminals on the right-hand side, and let's assume that our positive polarity reference is on top, okay? So anytime we're finding a Thevenin equivalent voltage, we are looking for an open circuit voltage, and conveniently enough, I have provided you with an open circuit at which we are going to make this measurement. I have also specified that the positive polarity reference is on top, which means that our Thevenin voltage, VTH, is simply this quantity. Now, how we go about finding this particular voltage is entirely up to us. But there are a couple of simple observations that we can make here that would arguably make things a little bit easier. So the first observation that I can make is that the current through the 10-ohm resistor is equal to what? Zero. The current through the 10-ohm resistor is 0 because the 10-ohm resistor is not part of a closed current carrying loop. So I'm going to make a couple of notes here real quick. So I know that this current is 0 amps. And from Ohm's law, I know that the voltage drop across the 10-ohm resistor must also be 0 volts. From that, I can say my Thevenin equivalent voltage is actually the voltage drop over the 6-ohm resistor. And I can do that by using Kirchhoff's voltage law around that right-hand path, right? If there's no voltage drop across the 10-ohm resistor, then VTH is the same as the voltage drop across the 6-ohm resistor. So this ugly-ish looking circuit here can really be analyzed as a single loop circuit because our controlling current Ix flows through all of the elements that are actually contributing to the behavior of this thing, okay? So if we write a KVL equation around this loop, we would have negative 20 volts plus 6 ohms times IX minus 2 IX plus 6 ohms times IX is equal to 0. And with a little bit of algebra, we can see that 10 IX is equal to 20 volts. And from here, IX is simply 20 volts over 10 ohms. It's 2 amps. Knowing what IX is, how do I get my Thevenin voltage? Pardon? Exactly right. So simple application of Ohm's law. If the current IX is the current flowing through the 6 ohm resistor over which we're taking our Thevenin voltage, Ohm's law tells us V Thevenin is 6 ohms times 2 amps is 12 volts. So to me, that circuit analysis was fairly straightforward. Okay. Now let's talk about finding I Norton. So by definition, the Norton current is the current that we see flowing through a short circuit when we short circuit the terminals that we found the Thevenin voltage across. Okay. So I'm going to short these two terminals together. And because V Thevenin was given as positive polarity on top, my Norton current should be in the direction down, like so. How do you guys think we should find this current I Norton? Yeah, let's just do mesh. We're trying to find a current. Mesh seems reasonable enough. So I'm going to call this mesh current IA. I'm going to call this mesh current IB. We do have a dependent source, so my controlling variable equation is going to be IX is equal to 6 ohms times IA minus IB. Let's make that A look more A-like. I don't have any current sources in this circuit, so I don't need to worry about any current relationships. So we're just going to have a KVL at mesh A, which is going to look like negative 20 volts plus 6 ohms IA minus 2 IX plus 6 ohms times IA minus IB is equal to 0. And because I want to have this all on one page, I'm going to have to do KVL at mesh B up here. Where this is going to be 6 ohms times IB minus IA plus 10 ohms times IB is equal to 0. Solving this, we'll get values for IA and IB. So let's see if I remember to bring a calculator. Doesn't look like I did. So somebody throw this system. Caden, what's up? For my controlling variable IX, because I made an asinine mistake. Thank you for noticing it. Okay. So what I found accidentally here was actually the voltage drop across the 6 ohm resistor, which is not what we are looking for. So that is very, very much a mistake. Thank you for pointing that out. Our controlling variable IX should just be IA minus IB. Good catch. Thank you very much. All right, so now let's throw the correct system into our calculators and then solve it. Anyone get a result yet? 40 over 17. What'd you get for IB? Could you throw that in decimal for me just so I can confirm it's the same thing I got the way I worked it 4 years ago?
IA got 2.359.
Okay.
IB I got 0.88.
All right, so that seems to be, I only have I2 or IB written down here as 0.882. I would imagine if we got that one, the other one is correct as well. All right, so working under the assumption that these values are correct, which all of you should be able to confirm by now. What is I Norton? IB. So let's put that over here. I Norton is simply IB, which is 15 over 17 amps. All right, so this is fairly straightforward. We found the Thevenin voltage by finding the voltage drop across our open circuited terminals. We found the Norton current by finding the current that flows through our short circuit terminals. Now we need to find our Thevenin. So how do we find our Thevenin? Well, what we learned on Friday is that we look into the open circuited terminals of our dead network to find the Thevenin equivalent resistance, all right? So here are my open circuited terminals. I'm looking in and I make this a dead network by turning off my voltage source. So what resistance do I see? Entertaining guesses. $13. So I'm assuming that you got 13 by saying that you have 10 in series with a parallel combination of 6 and 6, because that's the quickest way I can make 13 by looking at that. Unfortunately, Sully, you are incorrect. That's okay. This is a trick question. Anybody else? 12. How are you getting 12? All right. Also incorrect. Again, this is a trick question. The answer I'm looking for is how the hell should I know there's a dependent source in there? Okay. That dependent source prevents us from doing simple resistor combination techniques because it isn't a resistor. We obviously cannot simply ignore it. So we have to find some other relationships to use, okay? So the first relationship that we can use is simply Ohm's law. Our Thevenin resistance RTH will be our Thevenin voltage divided by our Norton current. Always, always, always. Okay. So in this case, that's going to look like 12 volts over 15/17 of an amp. Which I get to be about 13.6 ohms, and I believe there's some rounding error involved in there because I don't think those fractions come out that nice and neat, but maybe they do. Somebody tell me whether or not that seems reasonable based on these numbers. Exactly 13.6. Great. Okay. So if we know the Thevenin voltage and we know the Norton current, then we can find the Thevenin resistance, because if we know two of those quantities, we can always find the third one. That is one way to do this, okay? What if we didn't know one of those quantities? Is there a different means that we can do this? And the short answer is yes. What I'm about to teach you guys is what I call the test source method for determining resistance, okay? This is nothing more than how we talked about Ohm's law on our third day of class and how it was experimentally derived. So effectively, what we will do is we will take our network, make it a dead network by turning our voltage source off, and then we are going to apply a test source across the terminals. We are going to determine the test voltage across our network and the test current flowing into our network. And the ratio of these two quantities is R Thevenin. So effectively, the dead network that we're looking at is our material or device under test, circling back to how we described things at the beginning of the third day of class, okay? So this is nothing more than using Ohm's law as we experimentally determined it in order to find the resistance of this network. Now, applying the test source method, we get to choose whether or not we apply a voltage source and measure the test current, or we apply a test current source and measure the test voltage. We are going to do both of those things to show you that they're going to give us the exact same answer. They have to, okay? So let's start with a test voltage source. So I'm taking my network of interest, turning off my 20-volt source. So that's one thing that I want to be very, very clear about. In order to apply the test source method, we have to start with a dead network, okay? And then I am going to just attach a voltage source across the open circuit terminals of my network in question. I have multiple choices that I can make here, okay? I can choose the polarity of my voltage source. So positive polarity on top or positive polarity on bottom in this case. You guys tell me which one you want to work with. Positive polarity on top. I can also choose the magnitude of my voltage source. Because this is a linear circuit, the magnitude of the voltage source does not matter. We can choose literally any number. I am usually lazy and just choose 1. Okay, you can do anything, but 1 is lazy and simple. What our goal here is to determine this test current, I test. And then the ratio of 1 volt, our test voltage, divided by whatever we find for I test will tell us what the Thevenin equivalent resistance of this network is. Yes, sir. If you, all independent sources have to be turned off. So dependent sources have to be left on, all independent sources have to be turned off. Does not matter if it's an independent voltage source or some combination thereof, independent current source or some combination thereof. If it's a circle, turn it off. If it's a diamond, leave it alone. All right, so how are we going to solve for this quantity I test? Yeah, why not? We're solving for a current. Let's call this one I1. And this one I2. IX is going to be I1 minus I2. I didn't screw it up this time. Thank you again for pointing that out, Caden. Now I'm going to write my KVL equation. So let's start for KVL around mesh 1. That's going to look like 6 ohms times I1 minus 2IX plus 6 ohms times I1 minus I2 is equal to 0. I'm going to write my KVL equation around mesh 2. So that's going to be 6 ohms times I2 minus I1 plus 10 ohms times I2 plus 1 volt is equal to 0. And we can solve this system and find I1, I2, and if we're being lazy and leaving IX is just another variable, it's a 3 equation, 3 unknown system. So we won't need to do any substitutions. What do we get? What did you get, Nick? So yeah, for you, that's just going to be I1 minus I2. So that's 1/34. So 2/68 minus 5, or excuse me, plus 5/68 should be positive 3/68, I think. Anybody else confirm these numbers? All right. So what's I test? Negative I2. So that's 5/68 of an amp. And from this, R Thevenin is V test, which we chose, over I test, which we solve for. So this is going to be 1 volt over 5/68 of an amp, which looks like 68 over 5 ohms, which is exactly 13.6 ohms. We got the exact same result that we got knowing both the Thevenin voltage and the Norton current. Anybody have any questions about the analysis that we did here? Just good old fashioned mesh. All right. So now let's work this problem with a test current source. So I have my original network. I turn off my independent sources, and I'm going to apply a current source across the terminals of my system, where again, I can choose the direction of the current source that I apply. Let's arbitrarily choose up, and the magnitude of the current source that I apply, where I usually choose 1 amp. Now, one thing that I do want to point out here is if I had resistances that were in kilo ohms, I would probably choose 1 milliamp just so I didn't get abnormally large voltages and stuff like that all over the place. It doesn't actually matter at all. I just don't like seeing thousands of volts in simple circuits like this. It just bothers me. We are trying to solve for the quantity p-test. So how do you guys think we might go about doing that? Total, sure, why not? Okay. So I'm going to identify nodes real quick here. So this is one node, 2, 3, and 4. Which one do we want to be our reference node? The bottom, okay? So I'm going to call this VA, VB, and VC. Because we chose the bottom node as our reference node, we are going to have a super node. So we're going to take this current out of the super node, this current flowing out of the super node, and this current flowing out of the super node into account. When we get to that step, I'm just making sure that we recognize that we are going to have to do that. All right, so our controlling variable relationship is going to be IX is equal to VB over 6 ohms. We have a voltage relationship that is VB minus VA is equal to 2 IX. We have a KCL relationship at our supernode that is going to be VA over 6 ohms plus VB over 6 ohms plus VB minus VC over 10 ohms is equal to 0. And we also have a relationship from applying KCL at node C. VC minus VB over 10 ohms is equal to C minus V, yeah, -1 amps. We can solve this system for VA, VB, VC. Somebody please tell me what we get. Yes, sir. So actually, I think you're actually correct there, Daniel. So the mistake that I made, I should have had -1 amp is equal to 0, but I moved it to the other side when I shouldn't have yet. So you are correct. That should be +1 amps. Thank you. I'm just making all kinds of mistakes today. This is what happens when I take one class period off. I can't do nodal analysis anymore, apparently. Thank you for catching that. PHP 12/5. So, okay. All right, so assuming that those are correct, and it seems like it's going to be correct, our Thevenin resistance, RTH, is going to be V test over I test, where in this case, V test is simply our nodal voltage VC, 68/5 of a volt divided by 1 amp looks like 68/5 of an ohm, which is exactly the same as 13.6 yet again. So it does not particularly matter which of these three methods for determining the Thevenin equivalent resistance that we use. We just pick the one that's going to be easiest on us, right? So if we already know the Thevenin equivalent voltage and the Norton equivalent current, or if those two quantities are easy to calculate, we can just simply take the ratio of those two things. If one of those two quantities is going to be a pain in the ass, it might be more convenient for us to find the Thevenin equivalent resistance directly using one of the test source methods, and then use that to find our third quantity. Okay? So the last thing that I want to show you guys is that in some instances, not all of them by any stretch of the imagination, but in some instances, using a particular type of test source can make our lives slightly easier, okay? So let's say that we have the following network. And we wanted to find the Thevenin equivalent resistance of this network, okay? So one thing that I would like to point out is that because this circuit does not contain any independent sources, the Thevenin equivalent voltage and the Norton equivalent current are effectively meaningless because we don't have anything exciting our system, okay? So if you're ever given a circuit that only contains dependent sources, the only recourse you have is to use one of the test source methods, right? So this is the type of circuit that I would argue choosing your particular type of test source can make this problem more easy or more difficult. And so what I mean by that is we have a quantity here, IX, flowing through the 10 ohm resistor that is effectively going to be in parallel with our test source. So if we chose a test voltage of 10 volts, and we were solving for a test current, we know right off the bat that our current IX is 1 amp. And that eliminates a pretty reasonable part of the work that we have to do. Right? So if we know that IX is 1 amp, we effectively know there's a 2 volt drop over our dependent source. And so instead of having to write a system of equations using nodal or a system of equations using mesh analysis, we can actually just apply Kirchhoff's current law to figure out what I test is here, right? So I test in this case is going to be 10 volts over 10 ohms plus 10 volts minus 2 volts over 5 ohms. I'm saying essentially the current flowing in, which is I test, is equal to the sum of these two currents flowing out. No need to set up a system of equations whatsoever. A well-chosen test source gave us all the information that we needed without having to solve a system of equations. It will not always work out this way, okay? But there will be certain times where you can choose a particular type of test source, or maybe choose the polarity or the direction in such a way that will make your life easy, and you can do a trivial analysis like we just did here. All right, that's enough out of me for the day. So you've got in-class assignment stuff to work on. I will be happy to answer any questions you may have.